Okay, so I want to talk about weight. Weight. So the first thing we're going to do is we're going to recall that, recall that Newton's second law says F equals ma, and F stands for force. Force is a push or a pull on a mass. Okay, so we can say from this then that force, the amount of force is proportional to how much acceleration you'll get. Okay, and you know, how much force you need for a given acceleration is proportional to mass, right? So in other words, what that just means is for a given amount of force, if I have a high mass, I have a low acceleration, right? For a given amount of force, if I have a low mass, I have a higher acceleration, okay? Or another way to think about it is if I want a set acceleration, if the mass is large, I need a larger force, right? For a set acceleration, if I have a low mass, I need a lower force. So just keep that in mind. You know, really what we're kind of thinking about here is that mass is a way of connecting the amount of acceleration we'll get for a given force. Okay, it's kind of how I like to think about it anyway. So force is a push or pull on a mass. Last time we talked about the four fundamental forces of nature. Today we want to talk about a specific one, and that is gravity. And we want to talk about gravity on the surface of Earth. Later we'll learn about universal gravitation, but for now we're just going to talk about the surface of Earth and what happens with objects on it. So if we have something like this, okay, sitting on the surface, what we'll end up with is we'll get gravity pulling down on it, like that. And we calculate the amount of gravity based on how much mass we have here. And we might say that weight is equal to m times g. Now what this is just a special case of F equals ma. Okay, so the force of gravity is called weight. The mass is the mass in kilograms. And acceleration is the special acceleration g, right? G on the surface of Earth is about 9.8 meters per second squared, right? So that's the speed or the acceleration that you get near the surface of the Earth. All right, so there we go. We have a mass. It's got weight. The weight is pulling down. However, you know from Newton's second law that if you have, and I should have put a little net in there, if you have a net force, you're going to have an acceleration. Since this object is sitting still on the surface, clearly the F net is 0. So what that must mean is there is a counteracting force on this object, and that is called the normal force. Okay, so the surface, whatever this is sitting on, be it the floor or just the ground, must be pushing back up on the object to cancel out the downward force of weight. So we call this the normal force, Fn. Okay, and Fn is simply the exact same as mg, but in the opposite direction. So let's just summarize what we're talking about here. So weight. Weight is the force of gravity on a given mass. Okay, and weight points down. Okay, so if it has a magnitude and a direction, we can say obviously then that force is a vector value. Got direction and magnitude. And we can talk about the normal force. So this is the resistant or resistive upward force that surfaces provide. To weights, or to objects, I guess, with mass placed on them. So the normal force comes from the, if weight comes from the gravitational fundamental force, the normal force comes from, again, and this is just a quick review here, the fact that objects with mass are made out of atoms, okay, and the two atoms from the different surfaces repel one another because they have negative outer shells, right? So there's this electrostatic repulsion of like charges that prevent, one object from like melding into the other one. So, if you're sitting in a chair right now, what is preventing you from like passing through your chair? It's the electrostatic repulsion of the chair atoms to your butt atoms, okay? All right, so let's dive into this normal force because it's pretty important. It's what's preventing you and I from getting sucked into the earth, right? So let's start simple and let's build up. So the first thing and the easiest way to think about it is, well, what happens if I have a flat surface? If I can draw one here, in that case, right, like we said before, the normal force is just exactly in the opposite direction to gravity. So we've got normal force up, we've got gravity down. Oh, I should make it a different color. We've got weight down. I should call it weight. IB calls it weight. Depending what textbook you're looking at, they might call it the force of gravity. So we've got W down, and we've got F sub n saying the normal force up. And since these are vector values, if I sum them, I add them together tip to tail, I'll find that the net force, the F net, is 0. Now, we can say that the normal force is what's called a reactive force. In other words, the normal force will always be exactly as large as it needs to be. So what do I mean when I say that? So let's start and imagine this is an empty box. It's completely empty. So it's going to have a low weight, right? But then what if we add something to the box? Like, what if we start filling it with, like, not arrows. What if we start filling with, like heavy, like, golden coins or something? We just start, like, filling it up with weight, right? Whatever these are. You think of whatever you want to call them. Circular Easter eggs. I have no idea. Well, what's happening is we're increasing this, right? This is getting larger the more we add, and yet the box doesn't move. So because of that, the normal force must also be growing, right? So the normal force is a reactive force. It gets larger as weight gets larger. Why does it do that? Can you think about this? What we're trying to do here is we're trying to push this closer to that, okay? And a little bit later in physics, we'll kind of learn that if I have a charge, it's going to have an electric field around it, and that field gets stronger the closer I am to the charge. So in other words, as I push these closer together, the resistive force naturally gets larger because I'm trying to jam two things with electric fields closer and closer to each other. So this is a reactive force. It's reactive. It's always exactly as large as it needs to be. Now, there's obviously going to be a limit, right? If this represents a bridge or something, eventually I'm going to get so much weight that the bridge is just going to break. But until it breaks, the normal force will grow in exact proportion to the weight that's applied to it. All right, so the question is, what happens if I place my object, instead of on a flat surface, I put it onto a tilted surface? I want to know what's going to happen to my normal force, okay? So we're going to start to now draw what are called free body diagrams, okay? Free body diagrams. So before I get into the free body diagram here, I better explain what a free body diagram is. So free body diagram, or FBD. No making up your own what that could stand for is okay. So let's imagine that we have a helicopter. Okay, so a little helicopter. What does a helicopter look like? Like this. Okay, there's my helicopter. And it's flying along this way at a constant velocity. So a free body diagram will be a way of analyzing all the forces on this helicopter, right? So we know if it has a constant velocity, it's not accelerating in any direction, that all the forces on it must sum to 0. So the free body diagram is a way of thinking about all these forces. So we know that there's a force of gravity pointing down on this thing. We can call that weight, and that's mg. The props are counteracting that by spinning around, providing lift. We'll just designate that as F sub L. Okay, we'll call that the lift. The lift on the helicopter. If the helicopter is moving, there's going to be some wind resistance or drag. We'll call it drag. So we've got that going. FD, that's drag. And then if we have drag, we must have a forward push on this helicopter as well. We'll call that the thrust. Okay, thrust. I often call this one just FA, okay? Just because. Now, if we sum these, right, and remember how we sum them is we add them tip to tail, you'll find that this one cancels that and this cancels that. We end up with an F net equal to 0. Okay, now this picture is a free body diagram. Okay, so this is the free body diagram. It's just showing all of the forces acting on this helicopter, okay? So if I grab these and I make copies of them, if I can, uh-oh, no, I want to make a copy of you. Okay, so there's my lift. Actually, let's do it this way. Okay, there's my drag. So we had them all tip to tail, right? There's my weight. All right, so remember, it's from start to finish. Hopefully I did these the right size. What we should end up with is that we get right back to where we started. In other words, once I sum all these and I go from the original tail to the end tip, we should have a value of 0. There's 0 net overall force, okay? And as long as we add them tip to tail, it doesn't matter how we add them tip to tail, right? Put them any which way we want. I think it's just easiest to see them like this. The F net is 0. So now the next question is, right? There's no acceleration right now. Let's say we want the helicopter to go faster. How would we have to go about doing that? What would we do to make the helicopter go faster? We would have to increase the thrust, right? We'd have to take this value and we'd have to make it bigger, okay? We could do that in a helicopter, change the pitch of the blades, and all of a sudden we have a larger thrust than drag, and therefore we would have a net force and we would accelerate. In this case, I can circle the net force. It's simply this, right? From where we started to where we ended, this is our overall F net. Okay, so if F net is in the leftward direction, then we have an acceleration in the leftward direction, okay? If I want the helicopter to go down, well, I can't increase gravity, it just is what it is, but I could decrease my lift, and then it would start to accelerate downward. And it's just the interplay of all of these forces that are gonna dictate how the helicopter flies, right? If I put them all in balance, it just moves along constantly. If I increase one or the other, the acceleration is in that direction, or lower it, right? The acceleration is in that direction. If I want to slow down, I just dial back on my forward thrust, and all of a sudden, my acceleration is now back against the direction of my motion, right? And I have an acceleration on my helicopter. Okay, so that's kind of the general idea behind a free body diagram and a force analysis. Whatever's left over, whatever the net force is once I've summed all of the individual forces, is what is controlling the acceleration of my object. So if I go over here and I think about what forces are going to be acting on a block sitting on an inclined plane, we can start to draw them in, right? So the first thing, obviously, I think, is going to be the gravitational force. So let's draw that one in first. Make it blue. So that always points straight down, right, towards the center of the Earth. So let's label that. That is weight. Weight points down. Now, there's going to be a normal force here. However, the normal force does not point straight up. Normal force always works perpendicular to the surface that we're dealing with. Okay, so I'm going to draw that in right now. So it's like this, it's perpendicular to the surface. Perpendicular to the surface. Okay. So if I look at this picture, right, from experience, I know that there'll be a tendency for this block to slide down the plane, right? But there is no, in the way we've drawn this anyway, there's no way that it's going to move down the plane, right? There's one force pointing this way and one force pointing that way. But the key thing to think about is, well, what if we draw these forces tip to tail? Now what happens? If I move the weight up there, what you'll suddenly realize, hopefully, is that there is going to be a net force this way. Well, I don't want you to turn. Ow. Let's fix my drawing here. Okay, there's going to be a net force right here that aims parallel to the surface and down the plane. Okay. Now this is not the way it's traditionally drawn. It's actually more common to draw it like this. Jeez. Okay, where this represents the normal force. Having a lot of trouble moving my stuff around. There we go. Okay, and I don't want that to be that color. Okay, there we go. And then we say that there's an accelerating force parallel to the plane that's going to go right here. Okay, so that's the kind of like traditional way of showing this. So the force that's moving the object down the plane is this guy right here. We're just going to call that one FA. All right, so how are we going to analyze something like this? Well, we have a theta here. We have an angle here on this plane, right? Then that angle will be the same as this angle in here. I'm wondering if you're going to want me to prove that to you. Do you want me to prove it, or do you just want to believe it? It's not too hard to prove, actually. So basically, what's the easiest way to say that this is the same? So this triangle right here, right, is an equal triangle to this triangle. So the way to say that is, okay, so we've got a 90 degree here, right? So we've got a 90 here. That's 90. Then we've got an interior angle here, right, which is we'll call alpha. And remember, interior angles, right? Interior angles are always equal to each other. Okay, so we've got an interior angle there. Okay, so this angle and a 90, well, we have this angle and a 90 here, right? And also this angle and this angle are the same because these are parallel lines, so these interior angles are also the same. Okay, then this leftover angle must be theta because there's a little, this guy goes up there. So what we can say then is on this triangle, theta and theta will be the same. Hopefully that works for you. And then if that's theta, this will be like the alpha here as well. You can also call that, I think, opposite interior angles. I forget what the word for that is, but you got to think back to your geometry class for that. Okay, we can prove geometrically that this and this will be the same. So now what we want to do is we want to start defining these based on the theta value. So we're going to have to do some trig. So we know that weight is equal to m times g, right? But a theta here, we should see then that the normal force is the adjacent angle to this theta value, right? So if we look, this is the hypotenuse. So then the normal force should be weight times the cosine of theta, right? And then the accelerating force should be weight times the sine of theta. All right, so we write that down. The normal force is equal to W, which is weight, or mg if you want, right? Because weight is equal to mg cos theta. And the accelerating force down the plane, or parallel to the plane, is mg sine theta. So this is a way of drawing like a free body diagram, but also summing the forces and figuring out why this object would tend to move parallel or accelerate parallel to the surface. It's because the resultant force when you add weight to the normal force results in this leftover F net down the plane. Now, the one thing we're not thinking about and we haven't touched on is the concept of friction. For now, we can just say, yes, there will be some friction. It will aim like this because friction will always oppose motion. And apparently it's going to give me grief on drawing that. Okay, so there will be some friction opposing motion in real life. Often we ignore it but we can say that it is there, and we'll learn how to calculate that a little bit later. Okay, so the key thing here is understanding how to analyze something like this and figuring out the acceleration down the plane. Now, what kind of problem might you get from something like this? Well, I'll give you one. We'll try to solve it. Let's imagine that you have a frictionless surface, a ramp, essentially, a frictionless ramp, and you were to place an object on there. It's probably easiest to think of it with a circle because that's fairly close to frictionless, or closer anyway than a block would be. Okay, so we put a ball on the surface, and what I can say to you is this is theta. I can say to you, find the acceleration. If theta equals, I don't know, like say 20 degrees. Note, m equals 10 kilograms, and then m2, you're going to do it again with a 20 kilogram ball. Okay? Which one will have the higher acceleration? All right, so let's start to solve here. Okay, so let's draw in our free body diagram vectors. We've got our weight pointing down, like that. Oh, for goodness sake, just give me an arrow. Okay, we got our weight pointing down like that. Okay, we've got our normal force here like this. It's probably a bit larger than that. Okay, and then we've got our resultant accelerating force down this way. Like there, parallel to the surface. Okay, we know that we have a theta value here equal to 20 degrees. All right, so what we need to do is we need to find what is our FA, question mark. So we learned if weight here is equal to mg, then FA is mg sine theta. Okay, so that should be okay. FA equals mg sine theta. Solve for that. Mass was 10 kilograms. G, of course, is 9.8 meters per second squared. And we have the sine of 20 degrees. So that gives us about 33.5 newtons of force down the plane. And then we also know that F equals ma. So A should be equal to F over m. We have a force of 33.5 newtons. Divide it by the mass of 10. We should have about 3.35 meters per second squared of acceleration. Now let's do the exact same thing with our heavier ball. 20, 9.8 sine 20. So we get 67 newtons, which is exactly, I believe, double that. So if we do A equals F over m, we have 67 newtons divided by 20 kgs, and what? We get the exact same acceleration. So the mass of the ball is irrelevant because the force here increases because it's based on weight. As weight gets larger, this force gets larger, right? In exact proportion. So we can actually even do this without bringing weight into it at all, right? Remember at the end, we said A equals F over m. So we could say this. The overall force is m times A, right? We found that overall force as mg sine theta. So if we want the acceleration, mass appears on both sides. We can just do it like this. A equals g sine theta. Okay, so A in this case is g 9.8 times the sine of 20 degrees. You also always get 3.35 meters per second squared. And I think we'll leave it there.